do this. Obviously, if I can do a random challenge and response kind of capability to a user, I can authenticate that he's supposed to be there and be able to do this kind of a process, which is fine, except that within a small device with very little capability, how do you actually do that? And that's a problem that we've been working on for a while, and we believe we finally have gotten to the place where we have a very solid understanding in that space. So for instance, now we not only have the ability to control that connection point, but I can control levels of access. So for instance, I can give Joel, who is sitting there, access to be able to see registers 1 through 10, but maybe not modify any of them, just absolutely watch them but not see it. Maybe you can't control the program counter, so you can't change the way the program is flowing. You can just see some of the information. Maybe I don't let you see some of the key peripherals. I can then go to the next user, and I can give Bob over here the ability to control the program counter and some of the registers, but maybe he can't see some of the peripherals because that's not his responsibility. And I may have another guy who is the top person fully trusted in our organization. He's the only one that can run this tool to see absolutely everything. So I can control that in a granular fashion using this approach. The way we do that inside of an access manager, so I have this function called protected JTAG. I'm going to start by adding a random number generator, which a lot of these kind of chips typically either don't have or don't have a very good one. I'm going to be able to take a permission level from the outside world in, and I'm going to be able to then build a message. And a message, and I'll go through in a minute what that message looks like. I'm going to take a public key because I'm going to rely on some public key type infrastructure where I can take that public key and encrypt this message so that the device knows what it is, and the only one that can decrypt it, that can do anything with it, is going to be the person holding the private key out there in the infrastructure. That's going to then form my challenge. I can push that challenge out to the tools that are working on the middle. They can go to the secure server. The server can deal with it and then bring back a response. Inside the device, I can go through a verifier. I bring my original message into that verifier, the response into the verifier, public key is available to that verifier. If everything matches, then I can turn this permission controller on. I can set these levels, what signals can be controlled inside the processor, and once that happens, I reopen my JTAG interface at the appropriate level, allowing the appropriate feature sets to go out to these user devices. So some of the problems that we had to touch. First of all, you had to be able to meet the JTAG functionality within this capability. You had to be able to allow an appropriate user to have full access to this function without any restrictions for what they could normally do. Otherwise, you start to change every tool in the market space, which is not really feasible. You also wanted to have these different permission levels, be able to granularly change that in terms of I have different responsibilities for different parts of the organization. The other thing we very often talk about in doing protocols is what if there's a man in the middle and how do I protect against that? Well, remember the picture that I showed that my chip is over here and my server is over here. Not only might I have a man in the middle, I have to count on the man in the middle to make the protocol work. How do I maintain robustness in that kind of a solution? The other thing I have to be able to do is this has to be a hardware-only solution. I have talked with a number of people in the industry, and their approach was, well, why can't I just pass some certificates to my processor, check the certificates, and if the user has got a good certificate, I let him in. Well, remember what I started with, is that this particular tool can touch the processor from the time it comes out of reset. I'm watching the registers. I can single step it through. If the register that's holding the value that says I passed or failed my certificate check can be modified by the user at that point, which is part of the reason for this tool, they don't care whether they have a valid certificate or not. They're going to force the condition and they're in. So this really can only work if you have a piece of hardware that's on the system before your processor ever starts. And therefore, from a standpoint of dealing with real products, that means I have to minimize the gate count, the square area of the silicon, and I have to reduce the cost to make it a specific function. So in order to meet those requirements of trying to minimize the gate count and cost, I had to look at a protocol that was going to be very effective in hardware. It had to be small. We specifically looked at some of the elliptic curve mathematical functions because we thought we could meet some of those. But typically, if you're going to have to do those verification and encryption functions in elliptic curve, if you're familiar with that approach, typically you have either point multiplies, scalar multiplies, and inversion in order to be able to do those operations. And our problem was the inversion is huge in hardware. So we looked at this protocol from a function. How do I make it very secure? Can I move the inversion step out to the server that has a lot of horsepower and still maintain the security components down at the lower levels? And so we actually have a protocol that we believe will meet that in a secure fashion. And it also has the ability to handle these multiple levels during the process. So let me just walk through this briefly. Again, just kind of give you a flavor of some of the things that we did. If you have some interest, we can touch on it later. So I have 3 points to the system. On the left, I have a chip that's going to have this protected JTAG function. The middle, I'm going to have a set of workstation and tools that are going to be talking between the chip. And on the far right, I have my secure server. So within the protocol function, I'm going to use the following notation. I have P, which is a point on the elliptic curve. I have Q, which is my public key. And I may also have Q prime, which I'm not going to really talk about today because we also worked on a way to store only a piece of that public key for verification. Because if you have a programmable function that allows you to do that, those tend to be very large structures in silicon and very costly. We did work on a way that allowed us to streamline that down to about half what the existing art was in that space, so I could store a very small piece of key, yet guarantee the security proof that it was sufficient. In the middle, all I'm going to have is my user credentials on who I am and what capabilities that I possess. And then up at the server, I'm going to also have the A, which is my private key, and then I'm going to have the relationship that Q is equal to AP, which is a standard theorem within the elliptic curve map. So I'm going to start on the chip by generating 2 random numbers. I'm going to generate K and R, and you'll see how I use those in a minute. And then I'm going to accept a level L from the user at the workstation. And if I'm using this partial public key function, he's also going to process me the entire public key Q because he has a big disk on his workstation and he can pass that to me. There's a couple of techniques that we'll use to verify that the Q that he gave me is in fact the real Q that I'm expecting. Now this level is optional. In some cases you may only have an on-off condition, but in most of the devices we're concerned about, we typically have as much as 32 levels of permission based on these multi-core chips. And again, the Q is only going to be used if I'm using the partial storage. From there I'm going to build a message. I'm going to start with a header. This next element is the permission L times my public key. I'm going to use the X component of that. So if you're familiar with elliptic curve notation, I have an X, a Y, and a Z. And then I'm going to concatenate the random number R and the value of L. Now the reason why we do L and LP of X in the same function as part of the message is that gives me 2 different independent arithmetic statements that allows me to manage this man-in-the-middle condition. In terms of relative sizes, my R is going to be roughly 180 bits. X, I'm going to take about 100 to 112 bits, and then my L is going to be someplace between 20 and 32 bits. From there, I'm going to generate a challenge. And so if you're, again, familiar with elliptic curve functions, my challenge is going to be K, which was my random number, times P, which is my elliptic curve point, the message times KQ of X, which essentially is the encryption step of the message itself. And I'm also going to pass KQ of Z, which is going to allow me to avoid doing the inversions down here on my chip and move that up to my server. That challenge is going to go to the workstation. The workstation will then take that challenge, pass the original level that he's asking for and his user credentials up to the server. The server has the opportunity then to calculate M prime. So M prime is going to be MKQ of X. Remember, that's the middle term of the challenge. Divide that by KQ of Z, which was the third term of the challenge. And then it's going to calculate AKP, which is the private key that it owns, plus the KP, which was the first message of the challenge. If you divide all that back out, what you get is, assumably, the same message that you started with. From that message, we're going to extract L prime, R prime, and M prime. And we're going to verify that the user credentials is valid for the device they're talking to at the permission level that they're requesting, and that the level that they're requesting matches the level that the chip thinks that they're requesting, so we can make those 2 match in time. So L must match L prime, U must be valid, L prime and LPX must match, and also we had this little piece called the 01 header, which is in there for a couple of mathematical issues that we have during the translation of that protocol. If everything matches and the server decides that it's okay to allow and grant permission, it's going to calculate a verification token, which is M prime AKP. Again, M prime was extracted, and again, only the valid server that had the appropriate private key could get to that, times the private key times KP, which was originally came from the chip. The user just simply passes that to the chip, and the chip looks at MKQ, which is the numbers that it has, and if those 2 match, you can guarantee from a security and cryptography point of view that the server that held the private key is authorizing them to get access. If